All right, in section 5.4, we're going to discuss how to predict the polarity of molecules. In order to do this, you will need to have already predicted the shape of your Lewis dot structure correctly as well. In order to predict polarity, there are two things that we need to look at. The first is bond type, and the second is shape. In the drawing of nitrogen that we see on the picture, you can see that there's a triple bond, but more importantly, it is a non-polar covalent bond. The reason why this is a non-polar covalent bond is because we have two elements that are identical to one another. We can also look at the idea of electronegativity. Since each nitrogen is 3.0, 3.0 minus 3.0 we give you a difference of 0, which also tells us it's nonpolar covalent. In a nonpolar covalent bond, two atoms are shared equally. What we will learn is that any molecule that contains pure nonpolar covalent bonds will be a nonpolar molecule itself. So what does nonpolar mean? Nonpolar means that there are no distinct ends of charge. Because the electrons are shared equally, each nitrogen is equally pulling on the three pairs of electrons in between them. There's not one that is pulling stronger than the other, so there will not be any partial charges on this bond. In the molecule of hydrogen sulfide, we will focus on the fact that there are two sulfur-hydrogen bonds. If we take a look at that bond, you will notice that it is two different nonmetals, and thus it is a polar covalent bond. Sulfur is more electronegative than hydrogen, and so you can see in the dot diagram to the left that the pair of electrons that are being shared between hydrogen and sulfur will lie closer to sulfur because of that larger attraction towards the electrons. A polar covalent bond doesn't necessarily mean the molecule will be polar itself. We will have to look at shape to make that determination. When we look at the drawing of CH2O formaldehyde, you will see that there are actually two different bonds here. We have two carbon-hydrogen bonds, and we also have a carbon-oxygen bond that is double bonded. Both carbon-hydrogen bonds are going to be non-polar covalent. Even though they are two different nonmetals, we want to remember that the carbon-hydrogen difference isn't great enough to create partial charges. It's an exception to the rule, and we just need to remember that it's non-polar covalent. However, the carbon-oxygen bond is two different nonmetals, and so we would say that that is a polar covalent bond. So is this molecule polar or nonpolar? We will learn in the next few slides that shape makes all the difference. One of the ways that we can show how a polar covalent bond creates partial charges is to focus in on the electronegativity difference of the two atoms. We know that oxygen's electronegativity is greater than carbon's. And what that means is oxygen is going to pull the electrons closer to it. Because of that uneven attraction, oxygen is going to kind of take the electrons, and that gives it a partial negative charge, whereas the carbon is partially losing those electrons, and so it takes on a partial positive charge. One of the ways that we can demonstrate this separation of opposite charge is by drawing an arrow towards the more electronegative atom. And that arrow represents a dipole. A dipole is simply just separation of opposite charge. So let's do some quick practice in identifying if a bond is polar, and if so, we will draw a dipole to represent the separation of charge. In the first example, we have carbon-hydrogen. Since carbon and hydrogen are an anomaly, we must always remember that they are a non-polar covalent bond, and because of that, there will not be a dipole. We will say that both the carbon and the hydrogen are equally pulling on the electrons. However, OCl is a polar covalent bond, so we must decide who is more electronegative. Since oxygen is more electronegative, we will draw the dipole towards the oxygen. Remember that that means that the oxygen is partially negative and the chlorine is partially positive. Alright, the next one is FF, the fluorine bond. There are two identical nonmetals, so they must be nonpolar covalent, and thus they will have no dipole. And the last one is carbon and chlorine, and that is definitely polar. Chlorine is more electronegative, so we will draw the dipole in the direction of the chlorine, keeping in mind that carbon is kind of losing those electrons and chlorine is kind of gaining those electrons. Now that we have identified bond type and its importance in polarity, we now need to talk about how shape is important. Shape will determine whether those dipoles that we just drew will cancel or not. If they cancel, we will end up with a non-polar molecule. However, if the dipoles remain because the molecules are asymmetrical, then we will have a polar molecule. So remember that dipoles must move in equal but opposite directions in order for the forces to cancel. If this can happen, the dipoles will disappear and the molecule will be classified as nonpolar. So not every molecule with a polar bond will be a polar molecule itself. Let's take a look at the two pictures. On the left we have a diagram that is trigonal planar. Let's say this is boron trifluoride. And on the right we have a bent structure, and let's say this is hydrogen sulfide. Both molecules have polar covalent bonds within them, but there is something uniquely different between each. The diagram on the left, which is trigonal planar, is a symmetrical molecule, and in this case, all the dipoles will cancel out. When the dipoles cancel out, what that will mean is that there is no dipole remaining, and thus the molecule is non-polar. On the other side, the dipoles are moving in the same direction. And because they're moving in the same direction, they are not going to cancel, and that means that there will be dipoles present, there will be a net dipole, and that this molecule is polar. Remember that these dipoles are forces. The molecule on the left is really hard to see the cancellation because of the way it's drawn. But think of boron as a person, and that person has three triplets of equal strength pulling at 120 degrees apart from one another. If they all pull at the same time, the boron would never move, and that's because they are all equal strength and the dipoles cancel. However, if we think of sulfur as a person, and the two hydrogen atoms are twins of equal strength, and they both pull, they will actually move the molecule because of the extra added strength that is unevenly distributed. That means that one side of the molecule is going to be partially positive and one side of the molecule will be partially negative, making it polar. So we've just highlighted how important shape is. So if you don't draw a molecule's shape correctly to begin with, you could make a drastic mistake. If we take a look at the example of water on the left-hand side, you can see that it has been drawn as a linear structure. However, it is really a bent structure. If we were to code this, we would get an A, B2, E2, which correlates to bent. If we were to draw our dipoles, you can see that they are of equal but opposite direction, and so they would cancel out, and we would say that it is nonpolar. But that is not actually how the molecule presents itself. Really, the dipoles are both moving in the same direction, keeping that net dipole and making that molecule polar. Let's try a quick example. Let's start off by drawing the Lewis dot diagram for ammonia. I will simply draw this because we've already done this skill, and I will code it as an AB3E. So there's my central atom, there's my three bonding atoms, and there's my lone pair off the central. What that tells me is that this is a trigonal pyramidal molecule, and so I'm going to draw it correctly. Now that I know that, I can look at the nitrogen-hydrogen bond. I know that it is a polar covalent bond and that nitrogen is more electronegative. So I will draw the dipoles moving towards the nitrogen. Because they're moving in the same direction, that means that the dipoles will not cancel. The negative, partially negative nitrogen will be on the top, and the partially positive hydrogens will be towards the bottom. Because this molecule has two separate areas of opposite charge, it will be considered a polar molecule. So not only did it have polar covalent bonds, but it was also a polar molecule. When I draw the molecule for hydrogen sulfide, we end up getting this structure right here. If I code this, it would be an AB2E2. I have one central atom, that's my A, two bonding atoms, those would be my B2, and then two lone pair coming off the central, which is E2. What that means is my structure is really in a bent shape. Now that I know this, I'm going to look at each sulfur-hydrogen bond. Knowing that sulfur is more electronegative than the hydrogen, I will draw in my dipoles. Because both of those dipoles are moving in the same direction, they will not cancel out. That makes my sulfur partially negative and my hydrogens partially positive. And because of that, you can see that there is once again in this molecule two opposite ends of charge. And that's why this is considered a polar molecule. So once again, not only does it have polar covalent bonds, but it is also a polar molecule itself. If we draw the structure of carbon dioxide, you will see that it is actually a linear structure. You can code this as AB2. So I don't really need to redraw this. I am, however, going to draw in the dipoles. The dipoles for each carbon-oxygen bond will move towards the oxygens because they are more electronegative. And this is our first example where there are polar covalent bonds, but because the dipoles are of equal strength due to the fact that they are the same bond and they are moving in the opposite directions, those dipoles will cancel out and the molecule itself will be non-polar. So remember what non-polar means. That means that the molecule does not have distinct ends of opposite charge. In this case, the dipoles have canceled out due to the symmetry of the linear structure. So the molecule of carbon tetrachloride is actually a tetrahedral molecule. If I was to code this, it would be an AB4. We really should be drawing it like this. Carbon on the top, with the three chlorines kind of angling down like a tripod. Of course, the lone pair need to go around the chlorine. However, we're going to be able to see that dipoles can cancel each other out in a tetrahedral molecule a lot easier if we use the diagram on the left. So let's go ahead and draw in the dipoles. In this case right here, you can see that both chlorines are going to be more electronegative than the carbon, and that'll be the same in the north and the south position as well. Because these bonds are all the same, their dipoles are of the same strength, and all the dipoles are moving in opposite directions. So you can see that this one's moving right, and this one's moving left, so they cancel each other out. This one's moving to the top, this one's moving towards the bottom, so they cancel out as well. So even though this molecule had 4 polar covalent bonds, the dipoles canceled out, and it is considered a non-polar molecule. It would be kind of hard to see that relationship if I was to draw the dipoles if we were actually looking at the correct shape. But I want you to think of that boron trifluoride molecules a little while ago. If carbon was a person and it had 4 people of equal strength pulling at each 109.5 degrees apart from one another, and they pulled at the same time, the carbon atom wouldn't move. And that's because the dipoles, the forces, would all cancel out. So let's make this simple. Nonpolar bonds make nonpolar molecules. Polar bonds with a lone pair on the central atom, like the trigonal pyramidal shape or the bent, will most likely create a polar molecule. Polar bonds and no lone pair on the central atom, those would be the shapes of linear, trigonal planar, and tetrahedral. As long as all the terminal atoms are the same, they will make a nonpolar molecule. If any of the terminal atoms are different, then that will revert it to a polar molecule. So one last look at the basic shapes and the polarities. If we take a look at the first picture, you can see that this is a trigonal pyramidal. You can see that the dipoles are moving at 120 degrees apart from each other. Remember, this is a very hard one to identify, but because there are no lone pair off the central, This is a symmetrical molecule, and all those forces will equally cancel out. So this right here is a non-polar molecule. There is no net dipole moment. If we look at the diagram to the right, this is an example of a trigonal pyramidal. There is a lone pair off the central, and because of that, all the dipoles will be moving towards the lower end of the structure, creating a distinct end of charge between the molecule of positive and negative. So that means that this molecule will be polar. It will have a net dipole. If we take a look at the molecule right underneath it, once again, we have a central atom with two lone pair, and so we can probably predict that this will be a polar molecule. You can see that both dipoles are moving in the same direction, and they will not cancel out, giving us a molecule that has a partially negative and a partially positive end. And lastly, in the lower left corner, we have a linear structure, and this molecule is actually going to be non-polar. When we draw in the dipoles towards the more electronegative atom, because they are identical terminal atoms, those dipoles will cancel each other out, and you will not have two distinct ends of charge. There's no way we can cut this molecule in half and have a positive end and a negative end. Very similar to this one. There's no way we can cut this in half to have a positive and a negative end. That's why it is nonpolar. It has no distinct ends of charge as a molecule.